Okay, so I'm starting. Okay, so good morning all and welcome for today's talk. Again, as usual, if we have any questions or doubts regarding talk, regarding any concept during the talk, then you can post your questions on chat box. Also, the slides of this talk available on chat box as well as in our web page of this CATGT webinar series. And today we have Manisha Binjola from IIT Delhi, and she will be speaking on regular genus of PL4 manifolds with boundary. Over to you, Manisha. You can start.
Thank you, sir. Good morning, everyone. First, I would like to thank the organizers for giving me this opportunity. I will be talking on regular genus of PL4 manifold with boundary. I will define this term regular genus later in coming slides. Outlines are crystallization, its history, then what motivated us to write this paper, then main results, and then I will give two classifications of crystallizations and what can be further problems to be solved using this theory. Now, this first slide and most probably the second one as well would be known to many of you, especially who belong to algebraic topology. For others, I give some brief. A simplicial cell complex is collection of simplices which satisfies these two conditions. First of all, if we take a simplex, then its face should also be in that collection. And if we intersect two simplices, then resultant should be either empty set or a face or union of faces of both of the simplices. This is the definition of simplicial cell complex. Now I define star of V. Let V be any vertex. Then what we do, we take all the collection of simplices which has V as a vertex and we say this collection as a star of V. Now we take the simplices from the star of V which do not have V as a vertex. Then we call this collection as link of V. Now closed manifold. If link of each vertex is a sphere, then we say K is that simplicial cell complex. It represents a closed d-manifold. And if link is ball, at least one ball should be there, or sphere, then it represents a d-manifold with boundary. And in this theory, we use graph as a tool. So graph is like collection of vertices and edges. Now colored graph is, we color the edges of graph. So a graph with no loops is called a colored graph with these colors. Colors are denoted by 0, 1 to D. If any two adjacent edges have different colors, then it is called colored graph. Now, if degree of each vertex is same, we call it regular. And if we remove a fixed color, say K, from the graph, and we get regular colored graph, then we say that graph is regular with respect to that fixed color K. Now, this construction is the basis of this theory and very important one. I will use it again and again to visualize the things. So it says if we have a graph gamma, then we can always construct a simplicial cell complex. So it's a connection between topology and we are using graph as a tool. So if we have a graph, this means we have vertices and edges. We'll play around these two things only. For each vertex, we take a D simplex and label its vertices by the colors of edges in graph. Now, if second point is, if U and V vertices are joined by I colored edge, then correspondingly, we identify the faces, D-1 faces, which are opposite to I colored vertex. I give an example here for RP2. So this is the graph and this is corresponding simplicial cell complex. So first point states that we have 4 vertices in graph, then take 4 simplices. Okay. And look at this edge, say V3 and V4. So V3 and V4 are joined by red color edge. So in corresponding simplices, which are sigma V3 and sigma V4, join the edge, identify the edges which are opposite to red color vertex. That is, this edge and this edge gets identified. I hope it's clear. This is the most important thing. Now from the construction, we get a direct observation that if we take a subset of colors with k elements, then there is a bijection between simplices and the connected components of subgraph gamma restricted over B. So for better understanding, I take a particular case. Suppose we have a 5-colored graph. Okay? Let Gijk denote the number of components of gamma ijk. So we take gamma with colors ijk only. And kij is the notation which denotes number of edges with ij colored vertices in simplicial cell complex. So notice Gijk is the notation which is linked to graph and Kij is linked to simplicial cell complex. Now this observation states that Gijk equals Kpq. That is G with suffix equals K, the suffix of Gijk complement. Okay. Now suppose we want to see at G of gamma with C color removed. Okay. That is G C complement. Now from this observation, we get G C hat equals K of C hat hat. This means K of C complement complement. Okay. So G of C hat gives the number of C colored vertices in corresponding simplicial cell complex. Now these two things. In construction, we proved if we have a graph, we can always construct a simplicial cell complex. Now this point says, if we have a manifold with boundary, then there exists a graph representing that manifold. If in case of closed manifold, we will have a regular graph, and in case of manifold with boundary, we'll always have a graph which is regular with respect to a fixed color. Now, if we have a manifold, then it's obvious to ask a question, how many least number of vertices a simplicial cell complex representing that manifold can have. So in one of the paper, these are the researches which already have been proved. So this point says that in closed G manifold, we should have at least d plus 1 vertices. Okay. And if we have a manifold with H boundary components, then we should have dH plus 1 number of vertices. Now, on the basis of this thing, we formulate a definition of crystallization. So if suppose we have a graph gamma, which represents a manifold. Now, if the corresponding simplicial cell complex has the vertices which attains these bounds. Okay. In case of closed manifold, if number of vertices are d plus 1, then we say that gamma is a crystallization for closed manifold. And if in case of manifold with boundary, if number of vertices in corresponding simplicial cell complex attains this bound, that is, it has dH plus 1 vertices, then we say that gamma is crystallization for the manifold with boundary. And this theory is known as crystallization theory, which was born due to Pezzana. And in 1974, he proved that every connected closed PL manifold has a crystallization. And then Gagliardi extended this to manifold with boundary case. Now, let Gij, I have already told this notation, Gij denotes the number of components of gamma restricted over Ij colors. These are the notations. Now, proposition 3 states, if suppose we have a 4-colored graph with these colors 0, 1, 2, 3, and we have these conditions that G of gamma I hat equals 1. That is, we have exactly one vertex of each color 0, 1, 2, 3 in corresponding simplicial cell complex. Then gamma is a crystallization of some closed 3 manifold if and only if these two conditions are satisfied. Now next result is, if gamma is a d plus 1 color graph. Notice here it was 4-colored graph representing a 3 manifold. Now in this result, it's d plus 1 colored graph representing a d-manifold. Then we have this condition. And notice one thing, that this condition is analogous to this one. Looks like same almost. And this result is from this cited article. Let gamma be a crystallization for a manifold, possibly with boundary. Then we have this inequality consisting of rank of fundamental group and the number of components of these particular subgraphs, these three. We'll use these propositions in our main proofs. Now, if we have a graph and if its degree is d plus 1, then we call it an interior vertex. And if degree is 1 less, then we call it boundary vertex. This is the definition for interior and boundary vertices in graph. Now we construct a boundary graph. We give notation for this, for boundary graph as this. Now, as the name suggests, we are going to construct a boundary graph. So, and for graph, we need vertices and edges. So what should be the vertices for del gamma? It should be boundary vertices of gamma only. And then second thing, U1 and U2 will be joined by J colored edge in del gamma if the same vertices U1 and U2 in gamma are joined by alternate J and D colored edges. And we get a boundary graph. And again, notations, P bar denotes the number of boundary vertices, and this G dot suffix denotes the regular number of components, and G bar suffix denote the non-regular components of gamma with the same suffix as that of G bar. Now, next result is, if gamma is a crystallization of 4 manifold with H number of boundary components, then we have G dot ij4 greater than equal to H minus 1. So this G dot ij4 gives the number of interior edges. Okay, so we can visualize it as, suppose interior edges, like we have 2 boundary components. Okay, so interior edges, one edge, one vertex of this edge is on this boundary component, and another vertex should be on any other boundary component. Then only it would be interior edge. Now we know topological invariants play a very important role in topology. Here I define a new invariant called regular genus. Again, some papers are written to reach at this definition of regular genus, and I will summarize in a brief. So first of all, we have a color set, fix its permutation. Then a regular embedding is an embedding of gamma into some closed surface F if regions of surfaces are bounded by bicolor cycles. Suppose 0, 1, 2, 3 is a color set. We have this color set. Now, if regions, if one region is bounded by 0, 1, 0, 1 cycle, and other region is bounded by 1, 2, 1, 2, and then another by 2, 3, 2, 3, then this embedding is called regular embedding. So we can think it of as as we have a globe, and lines over it is our graph gamma. Okay. Now, for each cyclic permutation, the surface in which gamma is embedded, we denote its genus by rho epsilon gamma. And now, for each epsilon, we record the value of rho epsilon gamma and minimize it. Now it's fixed number, its and minimum number is called regular genus of gamma, denoted by rho gamma. Now for a manifold, we can have many crystallizations. We will have many crystallizations. And then we will calculate rho gamma, regular genus of gamma, from this definition, and then take its collection, then minimize it. And that number is called regular genus. And from these 2 papers, we get that the surface in which gamma is embedded has Euler characteristic in this form. So this is nice thing, that the Euler characteristic is depending only on the graph things. See, G dot and then P dot and P bar, where G dot ij and del G ij denote ij colored cycles in gamma and del gamma. And rho epsilon gamma, which I have discussed here, rho epsilon gamma, it comes out to be in this form. So totally on graph things. And we'll use these definitions only later. Now, motivation is if we have a closed 4 manifold, then we have a lower bound for regular genus. Now, if we have a manifold with boundary, then we have this relation, this inequality that regular genus is always at least regular genus of its boundary, and and always at least rank of fundamental group of M. So these lower bound problems have a significant role in combinatorial topology. And actually it gives a new classification problem. For example, if I say what happens if GM equals M, what happens if G of M equals, I mean regular genus of manifold equals regular genus of its boundary, what happens? So it again gives a new problem, classification problem, and I will give 2 classes of crystallizations later.
Manisha, sorry to interrupt in between. So, can you clarify one definition to me? The boundary of a colored graph.
Okay,
So,
sir.
yeah.
This is the thing. So for
Yeah. So when you
boundary,
say regular with respect to color D, there can be another color which with respect to what it can be regular, right?
yes, sir.
So when you say boundary of
So
something,
when we say, okay,
is
sir,
it is it
here,
respect to D only?
yes, sir. This graph, which we take, the boundary graph is, our boundary graph is obtained for those graphs only which are regular with respect to a fixed color. So we have
Yes.
already taken color D.
So in the notation it shows so right, like boundary of gamma with respect to something, right? Because when you don't denote it with D or something, it means that you can choose it with respect to anything and they are same.
Yes, sir. Yes, sir. Actually, suppose we have a graph which is regular with respect to some other color. Okay, then we can change the colors. It is independent of the that thing.
Oh, so it doesn't depend on the color D
Yeah.
that you're choosing.
Yes,
Okay.
yes, yes.
Okay. Yeah. Thank you.
So now we come to main results. Let gamma be a 5-colored graph, which represents a connected compact PL4 manifold with boundary. Then we have these 2 relations. Now, from the observation first, which came just after the first construction, we have told that Gij4 denotes K of Ij4 complement. Okay, so as we have only 5 colors, so G of Ij4, so suppose this is the color set. Okay, now Gij4 equals K of KL. Okay, so Gij4 denotes the number of KL colored edges, and G dot Ij4, the notation is for number of regular components. Okay, so G dot Ij4 equals number of interior KL colored edges. Now this del Gij equals number of KL colored edges in K of boundary gamma. K of boundary gamma is simplicial cell complex with respect to this graph del gamma. As we have constructed the del gamma, it is equal to number of boundary edges. So this is equal to number of interior edges. This equals number of boundary edges, and its sum equals number of total edges. So we have this proof, and on the similar basis, we can prove this second one also. Now we construct a graph for closed double manifold. So before that, what do we mean by double manifold? So we have a manifold with boundary. We take its another copy and then identify these 2 manifolds along with their boundaries. And as we did topologically, we will follow the analogous steps in using graphs. So we have a graph gamma for manifold with boundary M. Now we'll construct a graph, new graph gamma dash for the double manifold, which is closed. So we take a copy of gamma. We have 2 copies of gamma. one we name by gamma 1 and other one we name it by gamma 2. And then we label the vertices of gamma 1 by vi1 and gamma 2 by vi2. Okay. Now, so we have two copies of graph. So each consider each vertex. If it is interior vertex, leave it, do nothing. If it is boundary vertex, this means it has 1 degree less. Okay. This means 4 colored vertex is missing from this vertex, adjacent to this vertex. The same story happens with the another copy as well. Now what do? We'll join a 4 colored edge between these two vertices. Okay. And now we can see from the construction. Okay. Recall the first construction again. What is happening topologically? So boundary vertex and gamma give boundary facets in corresponding simplicial cell complex. And as we join two boundary vertices in by color 4 in graph, we identify the faces of boundary facets in corresponding simplicial cell complex. So this the thing which we get is nothing but closed double manifold. I hope it's clear. We are using that construction. Now lemma 8. Let gamma be a 5 color graph which represents a 4 manifold with boundary. Let gamma dash be the induced graph from gamma, which represents closed double manifold. So gamma dash here be constructed. Now, then these two conditions, these two paths hold. Okay, so before going to proof, recall the last construction again. So suppose we have a regular component of gamma, regular component of subgraph of gamma. Okay. Now, what will we have from, we have two regular components in two copies. Okay. Now, these two components are regular in the two copies. This means each vertex is interior vertex because each vertex is regular here. Okay. So with interior vertices, we don't do anything. So one regular component in gamma give two regular components in gamma dash. Okay. Now what happens with non-regular component? If we have a non-regular component, so we have another non-regular component which is copy of this component only. Now this is non-regular. This means we have at least one vertex which is non-regular. That is, we have one boundary, at least one boundary vertex here. So we join from the construction, we join those two vertices by color 4. And using the first construction, what are we doing? This means, okay, so we have two components, and as we join, so two components in two copies become one component in gamma dash. Okay. So as ijk, so this component is always regular. Non-regularity will come when 4 will come in picture. Okay. So G dash ijk, for ijk from this set, it becomes twice of Gij. And now G dash ij4 equals twice of number of regular components plus number of non-regular components, what I just told. Now twice of number of regular components means interior one. So G dot ij4, this notation I have defined, and non-regular component is G bar, which is nothing but the number of all the components minus number of regular components. Okay? So we get our result. And similarly, we can get this other part also. Now let gamma be a crystallization for manifold with H boundary components, and gamma dash is the same induced from gamma. Then we have a relation between number of vertices and G dash. So we express V gamma in terms of G dash ij. Here this chi-am is Euler characteristic. Okay. So let 2p be the number of vertices. Then these fi's are the standard notations for, it comes from f vectors, and it means that fi is the number of I simplices. Okay, so number of zero vertices. If we look at gamma, if we look at its simplicial cell complex with respect to gamma, so we have 4 colored vertex in interior, inside, okay? And 0, 1, 2, 3, 0, 1, 2, 3 vertices in boundary of gamma. So we have 4H vertices come from boundary and 4 colored vertex inside. So we have total 4H plus 1 vertices, okay? Now F4K gamma, I showed one example of RP2. There we take as many 4 simplices, as many vertices in gamma we have. Okay? So F4 equals twice of P. We have taken twice P. Now let X be the simplicial cell complex corresponding to gamma dash. Okay? Then the same thing, F0X equals 4H plus 2. So what is happening when we are taking double manifold? So we have this manifold here, 4 colored vertex inside and then these 0, 1, 2, 3 on boundary. Now when we take its another copy, but we identify the boundary components, okay? So boundary vertices here from this copy identify with boundary components from another copy, okay? But we don't do anything with the interior vertex. So we have one more extra 4 colored vertex which comes from the second copy. So the F0x equals 4H plus 2. And now F4x equals number of vertices in gamma dash, okay? Which is nothing but, as we are taking 2 copies of gamma, it's 4P. Now we have these 3 equations which tells the relation between Fi's, and these are called Den-Sommerwille equations. And as we solve it, we get these 2, and then again we get this one. Now we substitute the values of F0 and F4 from here, and we use this relation. We get it from the behavior of Euler characteristic under union. So we can easily get this. And then substituting here in this relation, we get this thing, our result. Now lemma 10. This is the most important result. Let gamma be a crystallization and G dash IJK denotes the number of components in gamma dash. So G IJK denotes the number of components in gamma IJK. G dash IJK denotes the number of components in gamma dash IJK. There should not be any. Now for any cyclic permutation, we get this relation. So rho epsilon gamma, which we define in the concept of regular genus, it equals this. Now let G dash Ij be the number of components. Okay, this is fine. Vertices of gamma we assume to be 2p. Then vertices of gamma dash become 4p. Okay. Now from equation 1, where we defined regular genus, we had this relation. Okay. Using these things, we get the 4th equation. Now gamma dash represents a closed double manifold. Okay. Then we can use proposition 4, which was for closed manifolds. So that's why we are taking this picture, double manifold, closed double manifold. Okay, so that we can use proposition 4, the known relations. So we have this relation. Now we'll use explicitly the values of IJK, and we have the 10 relations, okay, in this form only, which can be written as AX equals B. Now A is this, where X is this, and B is this. Now since A is invertible, so X can be written as A inverse B. We have A inverse in this form. Now we break B into 2 components, column wise. Okay. So this is the first component M, and this is the second one. So X equals A inverse M plus A inverse L. Now we have this black screen. Okay. G dash Ij equals this form. Okay, which is at the very above. G dash Ij is what? We have solved X, and this column consists of G dash Ij. So from here we get the value of G dash Ij. Now we take the summation with the required suffix. It comes this. Using lemmas 7 and 8, we have proved we get this thing, and then we substitute the value of this in equation 4, which was for chi epsilon gamma here. And then from equation 2, where we define regular genus concept, rho epsilon gamma equals this. And then using the value of chi epsilon gamma from here, these all are just calculations only. Okay. And then we, from lemma 9, we have this thing where we gave relation of number of vortices in gamma in terms of G dash. Now we substitute back. So we get rho epsilon equals this. Now we have a table. Now what will we do next? We'll solve this summation and this solution, this summation. And this table gives the entries for this summation only. Okay? One can solve it explicitly. And then from the table, we get this summation equals this thing. And this summation G dash RST, which we'll use here. So we have solved this one from the table. Now we are solving this. And if we open it, we easily get that this summation breaks into these two components. So here it's the number of total G dash RST. Here we have, it depends upon epsilon i's. Now we put back these two values in our, this value. Okay, and we get our result. Now, in last result, we proved rho epsilon in terms of G dash, and G dash comes from gamma dash. Okay, now we use our known lemmas to show that rho epsilon, we can write rho epsilon in terms of G's only, which is related to gamma only. We don't have to go to gamma dash. Okay, so, and it's easy. From last proof, we have this result. Okay, this one. And then we use the values again, the formulas which we have got, lemma 7 and lemma 8. We get this, and then by proposition 3 and using lemma 7 again, we get our result. It's easy, just calculation part. Now here I give new concept. Suppose removing one dipole. So what is one dipole? Let X and Y be two vertices joined by J color. Okay, so we have two vertices joined by J color. Now remove all the colors, all the J colored edges from graph. Now, if these X and Y are in different components, okay, then we say that we have a one dipole. Okay, one dipole theta, which consists of only these two vertices in this color J. Now cancellation of one dipole will follow these two steps. And as the name suggests, cancellation of one dipole. So first step is delete theta, delete X and Y vertices. Okay. Now if we delete these two vertices, so we have free edges which were earlier joined to these two vertices. Okay. Now second step is hang the same color edges together. And we can visualize it using the very first construction. So we are using that construction everywhere. So I can say that construction where we obtained a simplicial cell complex from graph, it's like it's an entrance. So if you want to come to this subject, this area, you use it. Okay. So from that construction, when we remove two vertices from graph, this means we are removing two simplices from corresponding simplicial cell complex. Okay. Here we have free edges when we removed. Here we have free d-1 faces. Free in the sense that we have some space left after removing these two simplices. Okay. And when we weld these edges, after welding, we identify correspondingly, we are identifying the d-1 faces. Okay. So the visualization, I think it's clear. And the important thing is when we cancel one dipole, it does not affect the topology of the manifold, whatever manifold it represents. Okay. And if you notice one thing, as I just showed using the gesture of my hands, when we remove one dipole, we are removing the number of vertices. Okay. So after removing one dipoles, we have lesser number of vertices in corresponding simplicial cell complex. So earlier we gave a graph for double manifold. Here we will give crystallization for double manifold. Okay. So these two steps are clear that we have constructed gamma dash earlier. And I've also discussed that that the gamma dash has 2 plus 4h vertices. So it has one additional vertex which comes as we the interior vertices do not get affected by this identification on using to construct a double manifold. Now, as we have, so what do we have in gamma? Okay, so look at the corresponding simplicial cell complex of gamma. So we have 4 colored vertex here and 0, 1, 2, 3 here. Okay, and here when we take its another copy, the same thing happens. Same things happen here. Okay, now these boundary vertices get identified. So after identified, each H component. So each component gives 4 vertices. Okay, so H components give 4H vertices. So we have we have H number of 0 colored vertices, H number of 1 colored vertices. Okay, and we have 2 4 colored vertices. This means we have H minus 1 number of 1 dipoles of these many colors, 0, 1, 2, 3 colored vertices. So H minus 1 number of 1 dipole of these colors and 1 dipole of 4 color. Okay, and if you look at the construction, we easily get first of all we denote G bar else the number of components of gamma bar with the same suffix. So G dash notation was for gamma dash and G bar notation is used for gamma bar. And we can easily get this thing, these relations using the construction. And one more thing. So we are getting crystallization for double manifold. But suppose we have a graph, we can always get a crystallization removing 1 dipoles, because removing 1 dipoles will we will get less number of vertices, and this the same thing we do for crystallization, we need for crystallization. Now we have this is the main result. Let M be a manifold with H boundary components and M and M bar be the rank of fundamental groups, okay, of M, and 2M is double manifold respectively. Then we have lower bounds for 3 lower bounds for regular genus of M. Now from proposition 5, since gamma bar is a crystallization we have constructed here. So from proposition 5 we get this thing, okay, and from the last thing we get these inequalities, and we put in lemma 10 here, and then using lemma 11 and 10 we get this thing, and then we put these things here, we get this thing, and we get the lower bound for rho epsilon gamma. Now rho gamma is the minimum of rho epsilons. So this is true for every epsilon. This means we get a lower bound for rho gamma. Okay, and using the same thing as regular genus of M is nothing but the minimum of rho gammas. So again, using the same thing, we get the lower bound for regular genus, which is this. Now second part, again we have only calculation things. So using lemma 11 we have this thing. Now since gamma is a crystallization, okay, so we have exactly 1 number of vertex of each color in corresponding simplicial cell complex, and using construction easily we can say that G of gamma del 4 minus 4 complement equals 1. So from crystallization this thing is clear, and then using proposition 5 we get this. Okay, these things all right. Okay, last we have that. Now the same things, we get a lower bound for regular genus of M. Okay, and then we go to part 3. We are using lemma 11. So lemma 11 is the most important thing we are using everywhere. Now using lemma 7, and these things again we have already done, used it in before parts before. Now we give a lower bound for rho epsilon gamma, and then again we get a lower bound for rho gamma, and it's for since it is true for any arbitrary crystallization, we get regular genus of M. Now we define 2 classes. So let gamma be a crystallization with this color set, we say that it is a weak semi-simple crystallization of type 1 if these conditions are satisfied. Okay? And we say M admits a weak semi-simple crystallization of type 1 if we have this representation, such representation for M. The second, the same thing, weak semi-simple crystallization of type 2. Crystallization is called weak semi-simple of type 2 if these conditions are satisfied. And we say M admits a weak semi-simple crystallization. Now corollary 3. So M admits a semi-simple crystallization. This is the definition. And here we give classes, these two things. So M admits a weak semi-simple crystallization if and only if the lower bound, the regular genus in this, see, this was the lower bound. If this regular genus attains this bound, okay? If and only if M admits a weak semi-simple crystallization. Okay? So these two parts come from the, these two parts are the lower bounds for regular genus from the last proof. Okay? So this is our corollary. From the proof of last theorem, and it's nothing but lemma 11. Yes. So rho epsilon gamma equals this. Now what we do, first we prove this part, if part. Suppose we have M admits a weak semi-simple crystallization. This means from the definition, we have a gamma which satisfies these conditions. Okay. Now we take another cyclic permutation of color set. Here, this 20 epsilon 2 0 3 1 4. Just for the notation to be clear, we can write it as in this form 20314. Now, so we need here in last definition. So G012 equals M plus H. Okay. So G012 means if we have epsilon 0, epsilon 0, epsilon 1, epsilon 2. So 0th position, 1th position, first position, second position, it equals M plus H. Okay. So G012, when we change this permutation, so 012 becomes 023. Okay. And then this Z023 we can put here. So this equals M plus H. And using this thing, we get rho epsilon dash. Okay. Rho epsilon dash equals this thing. Now, since regular genus is minimum of rho gammas and rho gamma is minimum of rho epsilons, okay, then regular we get an upper bound for regular genus of M. So this is an upper bound, and from the last result we have a lower bound, and it's the same. So we get equality here. Now we prove only if part. Okay. So regular genus. So suppose it is attained at this for this gamma and this epsilon. So only if part is, we have this, the hypothesis is this, okay? We have this thing. Now we have equality here, all right? Now we go back to last proof here. So rho epsilon equals this thing, okay? This means everything in between attains this equality, okay? And then using this thing, we again change the permutation here, okay? So that we can get the requirements according to our definition. It becomes 0, 1, 2 again, all right? So we change the colors of, we make a new graph, change the colors from gamma, and then we say that M admits this gamma bar, which is weak semi-simple crystallization of type. Okay. So this is our proof. Now, first thing we can do using these slides, we can always improve our lower bounds. So further researches, one thing is this can be done. Now, what happens in one of the slides I told that we gave the lower bound for regular genus. Regular genus is always at least regular genus of its boundary. Okay? And what happens if there is equality? So it is a conjecture that, so this is true if and only if M is connected sum of handle bodies. Okay? And for in dimension 4, this result has been proved, and we can do for higher dimensions. And there are some standard problems like regular genus is conserved. This property is conserved under the connected sum. And the most important open problem is smooth Poincare conjecture, if we can solve it using this theory. So these are some problems which one can go for it. And these slides were based on this paper, and these are the references used. Thank you, everyone.
Any questions or any comments? Okay, so if there is no questions, then I request each of you just unmute yourself and thanks the speaker by clapping. So thank you all for joining us, and thank you, Manisha, for giving a good talk.
Thank you, sir, for giving me this opportunity.
Yeah, you are welcome. So for the next half of this seminar, again, we will meeting on the next Wednesday at the same time. And the speaker for our next...
Sorry, not the same time, 10 a.m.
Oh, this
Next
is...
talk will be at
Okay,
10 a.m.
yeah, sorry. This is around 10 a.m. and the speaker is Yuaning Zhang from California University, and he will be speaking on filtering Grassmannian cohomology via case or functions. So again, for your information, the talks these talks are available also in our YouTube channel, CATGT. You can find the previous talks also there. So yeah, thank you again all, and thank you, Manisha, for joining us.
Thank you, sir.